All right, folks, welcome to the third lesson of the third unit here, the third and final lesson. It's a very, very quick unit, so we'll be uh, getting into the review and the exam after this. The last topic that we have is tolerance and acceptable values. Basically, what that's going to be doing is we're going to be looking at the precision of a measurement, the uncertainty involved within that measurement, and evaluating what the tolerance is. Tolerance down here being the difference between the max and the min, and what the acceptable values are. So that would be your max and min values there. Now we're going to introduce a couple of formulas here just so that we can describe these tolerances and acceptable values. The first is this precision and the uncertainty is half of the precision, which is what we've dealt with before. You'll notice the measurement plus or minus uncertainty right there. We've seen that before as well. The new one, however, is this percentage error right here. Okay, so if we're talking about the percentage error in a measurement, all it is it's just your uncertainty divided by your measurement multiplied by 100 to give you your percentage. Okay, seems to make sense, but if you have a smaller percentage error, it's a better measurement, right? It's more favorable. You're closer to that truer value. So we can go through and do a couple of problems here. So a part in a machine shop has a maximum allowable dimension of 14.28 millimeters and a minimum dimension of 4.16. We want to figure out what the tolerance is. Okay, well, tolerance is just max minus min. Okay, and our max value, it said a maximum allowable value of 14.28 millimeters and a minimum allowable of 14.16 millimeters, which gives us a tolerance of 0.08 millimeters, like so. Okay, that's all it is. Next, if we've got the length of manufactured pipe given as 16.056 meters with a tolerance of 0.0007, we want to figure out if the following pieces are acceptable. So in order to figure out if they're acceptable, we need to figure out what our max and min values are. Okay, your tolerance is just your max minus your min. So your uncertainty here is just your tolerance divided by 2. Okay, now 0.0007 over 2 is 0.00035 meters. So then from that we can figure out our max is 16.056 meters plus 0.00035 meters, or 16.05635 would be our maximum, and our minimum then would be 16.056 meters minus 0.00035 meters, or 16.0556 or 65, sorry, meters, like so. Okay, so now that we have those maximum and minimum values, all we have to do is figure out if these values up here are between those two max and min values. So we've got 16.05672, 065 or 5672 is above our maximum, so that is an unacceptable piece. Next one, 0.055757, okay, 0.055557 is above the minimum, so that would be an acceptable value. 16.05605, 0.560 is less than our maximum, so that one would be acceptable. And then we have 0.05585, 0.0558, that's above our minimum, so that would be a yes. And then 0.05535, 553 is less than our minimum, so that would be an unacceptable value. All right, next one here. Basically, we're just going to go through and fill everything in based on what we have here. So our measurement on the first one, our precision, we can see is 0.1 degrees Celsius. Our uncertainty then would be 0.05 degrees Celsius. Our tolerance interval, this thing, is just your measurement plus or minus your uncertainty. Okay, that's all your tolerance interval is. So you would take your measurement, 25.2 degrees Celsius, and plus or minus 0.05 degrees Celsius. So from there, then we can figure out the range of the true measures. Well, if we take the minimum value would be 25.15 degrees Celsius, and our maximum would be 25.25 degrees Celsius. Lastly, we can figure out what our percentage error is by taking our uncertainty and dividing it by our measurement. So our uncertainty is 0. Okay, why are you doing that? Our uncertainty is 0.05 degrees Celsius, and our measurement was 25.2 degrees Celsius, which would give us an uncertainty in our percentage error of 1.98%. Be 0.0198 or 1.98%, like so. Same thing as before, we can do the same for 1 3/8 of an inch. Okay, when you're given a fraction like this, the precision is the denominator, so over 8, and it'd be 1. So 1/8 of an inch would be our precision here, which means our uncertainty is half of 1/8 of an inch, or 1/16 of an inch. So then our tolerance interval would be 1 3/8 of an inch, plus or minus 1/16 of an inch, like that. So then our range of true values would be 1 5/16 as our min, to 1 7/16 of an inch for our max. Lastly, we can find our percentage error by taking our uncertainty. Oops, I forgot to put units on my uncertainty. Of 1/16 of an inch, and divided by our measurement of 1 3/8 of an inch. And we can do that. That would give us 0.0455 or 4.55% as our percentage error. Okay, lastly, 9.05 seconds. Right there we have our precision of 0.01 seconds, which means our uncertainty is 0.005 seconds, which means then that our tolerance interval would be 9.05 seconds plus or minus 0.005 seconds, like so. That makes our range, our minimum value would be 9.045 seconds, and our max would be 9.055 seconds, like so. And lastly, our percentage error is just our uncertainty. Stop doing that, please. 0.005 seconds divided by our measurement of 9.05 seconds, which would give us 0.0055 or 0.55%, like so. Okay, so that's how you do those tables. They're pretty straightforward. Next, we want to order the measurements from question 4 from least certain to most certain. Okay, least certain, we're looking for the lowest we're looking for the highest percent error. And the most certain would be the lowest percent, like so. So the lowest one that we have is, or the highest one that we have, sorry, is the 1 3/8 of an inch. The middle one is our 1.98%, which is 25.2 degrees Celsius, and our max then is the 0.55%. The most certain is the 0.55% or 9.05 seconds, like so. All right, next. Speedometers in most vehicles have a percentage error of plus or minus 5%. The reading on the speedometer of the car is 90 kilometers an hour. We want to figure out what the maximum possible speed is. Now, if we go and we start with our uncertainty over the measurement equals percent error, is what straight off your formula sheet there. We can substitute what we know. Okay, this is our percent error. And we have this guy right here is our measurement. So we can figure out what our uncertainty is, which will help us figure out the minimum possible using our tolerance interval. So our uncertainty, substituting what we know, uncertainty divided by the measurement of 90 kilometers per hour is equal to our percentage error, which written as a decimal is 0.05. Okay, so uncertainty then, oops. All we have to do here is multiply both sides by 90. Okay, 90 here, come on, 90 here and 90 here cancel, which would give you 4.5 kilometers per hour as your uncertainty. Then you can write your tolerance interval as 90 kilometers per hour plus or minus 4.5 kilometers per hour, which to find the min then, that would just be 90 kilometers per hour minus 4.5 kilometers per hour, which would give you 85.5 kilometers per hour as your minimum possible speed. Okay, your tolerance then is just your maximum value minus your minimum value, which is also twice your uncertainty. Okay, so uncertainty times 2 is 2 times 4.5 kilometers per hour, or 9 kilometers per hour would be the tolerance there. Okay. Next one, speedometer in an antique car has a percent error of 8.5%. The reading on this speedometer is 65 kilometers an hour. We want to figure out the maximum and minimum possible speeds for this antique car. So this is the exact same thing as what we did before. The uncertainty over 65 kilometers an hour is our percentage error, or 0.085. So then our uncertainty is just 0.085 times the 65 kilometers per hour, which is equal to 5.525 kilometers per hour, like so. So then we can figure out what our max and our min are by adding our uncertainty to our, from this guy here, we know that our tolerance interval is 65 kilometers per hour, plus or minus 5.525 kilometers per hour. So then we can figure out what our max is by just adding those. .65 kilometers per hour plus 5.525 kilometers per hour, which is equal to 70.525 kilometers per hour. And then our min would be 65 kilometers per hour minus our 5.525 kilometers per hour, or 59.475 kilometers per hour. So that is the maximum and the minimum possible speeds for the old antique car, because it's got a very high percentage error. So then based on that, we can figure out the tolerance. Remember, your tolerance is just your max minus your min, which is 70.525 kilometers per hour minus the 59.475 kilometers per hour, or 11.05 kilometers per hour. Okay, so next we've got another little handy formula here. Your nominal value is just your max plus your min divided by 2. It's the average of your max and min. It's trying to find that middle value. That's what your nominal value is. So if we are given maxes and mins here for the next question, 15.2 degrees Celsius and 12.4 degrees Celsius, all you have to do is find your nominal value, which is your max, plus your min over 2, which would be 15.2 degrees Celsius plus 12.4 degrees Celsius divided by 2, which would give you 13.8 degrees Celsius. From that, then we know we also know our tolerance is our max minus our min, which is 15.2 degrees Celsius minus 12.4 degrees Celsius, which is 2.8 degrees Celsius, which means that our nominal value, or our tolerance interval here, is then our nominal value, which is 13.8 degrees Celsius, plus or minus half of our 2.8 degrees Celsius, or 1.4 degrees Celsius, like so. Oh, 1.9, sorry. No, it's 1.4. 1.4 degrees Celsius. My notes are wrong, apparently. Same thing as before. We can figure out we want to figure out nominal value plus or minus the half of the tolerance. So if we have a maximum of 25 inch and a min of 21, first thing is our nominal value is just 25 inches plus 21 inches, all divided by 2, which would be 23 inches. And then our tolerance is 25 inches minus 21 inches, or 4 inches. So then our nominal value plus or minus half of our tolerance then would be 23 inches plus or minus 2 inches, or half of 4 there. Okay, last one, 4.25 centimeters for a max and 3.65 for a min. So same thing before, our nominal value would be 4.25 centimeters plus, that's getting really irritating, plus 3.65 centimeters, all divided by 2, would give you a nominal value of 3.95 centimeters. And we can then find our tolerance of 4.25 centimeters minus 3.65 centimeters, which is equal to 0.60 centimeters. So then our tolerance interval would then be 3.95 centimeters plus or minus our half of our tolerance, or 0.3 centimeters, like so. All right, next one here. Mackenzie is working on making caramel candles. The recipe says to use a candy thermometer to monitor the temperature of the sugar mixture. If it's not heated enough, the candles will not take their shape, and if they're heated too much, the candles will be too firm. The sugar mixture must be between 245 and 250. So what's the tolerance? Well, it's just your max minus your min. So 250 degrees Fahrenheit minus 245 degrees Fahrenheit, which is 5 degrees Fahrenheit. So then we can write the acceptable temperature range in the form measurement plus or minus uncertainty. In order to do that, though, we have to find what our measurement is right here. Okay, our measurement is just our nominal value. So to find our nominal value, it was just your max of 250 plus your min of 245, all divided by 2, which is 247.5 degrees Celsius. So then you have, oh, there's this degrees Fahrenheit. This is degrees Fahrenheit. Apparently I'm not even using the right units. Degrees Fahrenheit, there we go. So now we have our tolerance, we have our nominal value, so our measurement plus or minus uncertainty would just be 247.5 degrees Fahrenheit plus or minus half of our tolerance, which is 2.5 degrees Fahrenheit, like so. Okay, so the next one here, we've got Serena is making a new front door for her house. In order for it to fit properly in the frame, the door for her house must have a nominal value of 24 inches and a tolerance of 1/8 of an inch. So then to figure out the maximum and minimum values of the door, okay, so the first thing I would do is write this as the nominal value plus or minus half of our tolerance. Half of 1/8 of an inch is 1/16 of an inch, like so. And then from that, we can find our max as 24 inches plus 1/16 of an inch is 24 and 1/16 of an inch. And our min is 24 minus 1/16 of an inch, which would be 23 and 15/16 of an inch, like so. Okay, Mike is making custom cabinets. The front face of the drawer must have a width between 17 and 15/16 of an inch and 18 and 1/16 of an inch, and the height between 6 and 15/16 and 7 and 1/16 of an inch. We're going to figure out what the nominal dimensions of the drawer face are. So we'll look at the width first. Width nominal would be 17 and 15/16 of an inch plus 18 and 1/16 of an inch divided by 2. Okay. To add those two together, you'll notice 1/16 and 15/16 gives you 16/16, which is 1. So 1 plus the 17 plus the 18 is 36 divided by 2 is 18 inches. And then we can do the same thing for the length. Length nominal is 6 and 15/16 of an inch plus 7 and 1/16 of an inch divided by 2, which same thing would be 14 as a total to give you a nominal value of 7 inches. So then we can figure out what the tolerance of each of the measurements are. Remember, tolerance is just your max minus your min. So the tolerance, we'll go width, tolerance is your max minus your min, so 18 and 1/16 of an inch minus 17 and 15/16 of an inch to give you 2/16 of an inch, or 1/8 of an inch if you were to simplify that fraction. And then you can do the same thing for the length tolerance, which is 7 and 1/16 of an inch minus 6 and 15/16 of an inch, which would give you again 2/16 of an inch, or 1/8 of an inch. So then we can write it in the nominal value plus or minus half tolerance. Okay, so for the width, our nominal value was 18 inches, plus or minus half of our tolerance is 1/16 of an inch. 1/8 divided by 2 is 1/16. And our length then would be 7 inches plus or minus 1/16 of an inch, like so. Okay, the very last one, an electrical resistor has a resistance with a nominal value of 100 ohms and a tolerance of 3%. Okay, just so you don't get confused, this has units of Greek letter omega. It's kind of like a, I don't even know what it's like, but it's a Greek letter omega. It's the symbol for ohms, and I'm going to be using that for my units here. But it's got a tolerance of 3%. Well, that's a percentage. We don't want 3%. We want to figure out what it is in ohms. So just to start with that, we would have to go 100 ohms. Come on, pen, work with me here. 100 ohms times 0.03, or 3 ohms would be the, that's a terrible omega. 3 ohms as your tolerance. So then we want to figure out the range of acceptable values. That's your max and your min. So we would take our nominal value, the range of acceptable values is just your tolerance here. So that would be 3 ohms. Okay, we can write that as a nominal value plus or minus our half of our tolerance. And our nominal value is set as 100 ohms, plus or minus half of our tolerance would be 1.5 ohms, like that. From that, we can get that our max is 101.5 ohms, and our min is 98.5 ohms, like so. Okay, so that's the measurement unit. Pretty straightforward stuff. Only a couple of things for you guys to remember. You should be able to do the third assignment and the third quiz now. And make sure you do the review as well, because you need to be able to do that for the exam, which will be coming up right away as well. So if you have any questions, let me know. Otherwise, you know what to do.